the M1. Garand was more than a rifle. It was General George Patton's greatest battle implement ever devised, a semi-automatic weapon that gave American infantrymen a staggering tactical advantage over enemies still clutching bolt-action rifles. Between 1936 and 1957, over 4 million M1 Garands rolled off production lines. But the story of how they were made is a saga of industrial might, engineering precision, and wartime desperation that turned a Massachusetts arms factory into the beating heart of American firepower. Before a single trigger was pulled in anger, the M1 Garand began its life deep in the earth, in the iron ranges of northern Minnesota and the coal fields of Pennsylvania. The Mesabi Range, stretching across the frozen wilderness near Hibbing, held some of the richest iron ore deposits on the planet. During the war years, open-pit mines operated around the clock, with steam shovels biting into the reddish-brown earth and loading 20-ton chunks of hematite onto rail cars. The ore contained roughly 60% iron by weight, and mining companies extracted it in quantities that would have seemed impossible just a generation earlier. In 1943 alone, the Mesabi Range produced over 70 million tons of iron ore, much of it destined for weapons manufacturing. The ore traveled south on dedicated rail lines, passing through Duluth and Chicago, before reaching the steel mills of Gary, Indiana, and Pittsburgh, Pennsylvania. These journeys covered hundreds of miles and required coordination between multiple railroad companies, all while German U-boats prowled the Atlantic and disrupted shipping lanes that might have brought foreign steel. The American military-industrial complex had to be self-sufficient, and that meant moving raw materials across a continent with the urgency of a military campaign. At the steel mills, the real transformation began. Blast furnaces towered over the landscape like industrial cathedrals, their tops wreathed in smoke and flame. Workers fed the furnaces with alternating layers of iron ore, limestone, and coke, a purified form of coal that burned hot enough to melt rock. The chemical reactions inside these furnaces were brutally simple, but required precise control. As temperatures climbed past 3,000 degrees Fahrenheit, the iron ore gave up its oxygen atoms, and molten iron pooled at the bottom of the furnace, while impurities rose to form slag that could be skimmed away. But this pig iron was too brittle for rifle barrels and too impure for precision parts. It had to be refined further in Bessemer converters, or open hearth furnaces, where controlled blasts of oxygen burned away excess carbon and other unwanted elements. The steel that emerged from this process was an alloy carefully balanced for strength and machinability. For rifle barrels, the specifications called for a medium carbon steel with chromium and molybdenum added for heat resistance and durability. Every batch was tested, and metallurgists scrutinized the grain structure under microscopes to ensure it met military standards. The molten steel was poured into molds to create ingots weighing several tons each. These ingots cooled slowly, their crystalline structure forming over hours, and then they were reheated in soaking pits before being passed through rolling mills that squeezed and stretched them into long steel bars. The bars were cut to length, sorted by grade, and shipped to the Springfield Armory in Massachusetts, and later to the Winchester Repeating Arms Company in New Haven, Connecticut, both of which had been contracted to manufacture the M1 Garand in quantities that would have overwhelmed any single facility. Springfield Armory was the epicenter of M1 Garand production, a facility that dated back to George Washington's era, but had been modernized into a sprawling complex of machine shops, heat-treating facilities, and assembly lines. The factory covered over 50 acres, and during peak wartime production, it employed more than 13,000 workers operating in 3 shifts that kept the machines running 24 hours a day. The noise inside was a symphony of industry, the rhythmic clanging of drop hammers, the high-pitched whine of precision lathes, the hiss of steam-powered presses, and the constant rumble of overhead conveyors moving parts from one station to the next. The rifle barrel was the heart of the weapon, and making one required extraordinary precision. Steel bars arrived at the barrel shop, where they were first heated in gas-fired furnaces until they glowed cherry red. A drop hammer, weighing several tons, slammed down repeatedly to forge the bar into a rough barrel shape, compressing the metal and aligning its grain structure for maximum strength. The forging process was brutal and loud, and each impact sending shock waves through the concrete floor and filling the air with the smell of hot metal and machine oil. Once forged, the barrel blanks moved to the drilling department. Here, massive vertical drill presses used tungsten carbide bits to bore through the solid steel, creating the barrel's interior channel. The process was achingly slow, taking over an hour per barrel, and required constant cooling with cutting fluid to prevent the bit from overheating and losing its edge. The barrels emerged with rough interior walls that had to be smoothed and sized through a series of reaming and rifling operations. Rifling was where the magic happened. The inside of the barrel received a series of spiral grooves that would impart spin to the bullet, stabilizing it in flight and dramatically improving accuracy. Springfield Armory used a method called button rifling, where a hardened steel button with the negative image of the rifling pattern was forced through the barrel under hydraulic pressure. The button cut or displaced metal as it traveled, leaving behind 4 grooves that twisted one turn every 10 inches. The precision required was staggering. The grooves had to be uniform to within thousandths of an inch, or the rifle would shoot wild. After rifling, the barrels were heat-treated to harden the steel and relieve internal stresses. They were heated to 1,550 degrees Fahrenheit in electric furnaces, held at that temperature for precisely timed intervals, and then quenched in oil baths that cooled them rapidly. The sudden temperature change transformed the steel's crystalline structure, making it harder and more wear-resistant. But heat treating also introduced warping, so every barrel had to be straightened on hydraulic presses, while machinists checked them against optical comparators that could detect deviations measured in 10,000ths of an inch. The receiver, which housed the rifle's operating mechanism, presented different challenges. It started as a steel forging that weighed over 12 pounds, but would be machined down to just over 2 pounds of finished metal. The excess material wasn't waste. It was insurance against defects, and provided enough stock for the intricate cuts and drilled holes that would transform a lump of steel into a functional receiver. The machining process took place on multiple stations, each equipped with specialized cutting tools. Vertical milling machines carved out the receiver's distinctive profile into creating the magazine well, where the 8-round en-bloc clip would seat, the ejection port, where spent cartridges would fly out, and the mounting points for the barrel, trigger group, and operating rod. Every cut had to align perfectly with every other cut, because even a small misalignment could prevent the rifle from functioning. Drilling the receiver required particular care. The bolt had to slide smoothly through the receiver's raceway, and the tolerances were so tight that drill bits had to be replaced frequently to maintain sharpness. Machinists used gang drills that could bore multiple holes simultaneously, speeding production without sacrificing accuracy. The holes for the trigger pins, hammer pins, and rear sight required reaming to exact dimensions, and go-no-go gauges checked each one. The bolt assembly was another masterpiece of precision manufacturing. It started as a cylindrical steel forging that would be turned on lathes to create the bolt body, with its locking lugs and extractor groove. The bolt face, which had to withstand the pressure of firing, was cut with a recessed area for the cartridge base and a channel for the firing pin. The locking lugs, 2 rectangular protrusions that engaged the receiver to lock the bolt closed during firing, had to be cut to exact dimensions and then heat-treated to increase their hardness. The firing pin was a separate component, a slender steel rod with a pointed tip that would strike the primer of the cartridge. It was hardened through a process called case hardening, where the surface of the steel was enriched with carbon and then rapidly cooled, creating a hard shell over a tough core. This prevented the firing pin from mushrooming or breaking under repeated impacts. The operating rod, which connected the gas system to the bolt, was forged from a single piece of steel and machined to include a piston head, a connecting rod, and a cam lug that controlled the bolt's rotation. The gas system of the M1 Garand was its most distinctive feature and the source of its semi-automatic capability. When a round was fired, some of the expanding gases were diverted through a port in the barrel and into a gas cylinder mounted beneath the barrel. These gases pushed the operating rod rearward, which unlocked the bolt, extracted the spent cartridge case, cocked the hammer, and compressed the operating spring. As the spring expanded, it drove the bolt forward, on stripping a fresh cartridge from the clip and chambering it, ready to fire again. Making this system work reliably required exquisite attention to detail. The gas port had to be drilled to a precise diameter. Too small, and the rifle wouldn't cycle. Too large, and it would batter itself to pieces with excessive recoil. The gas cylinder had to be perfectly aligned with the barrel, and the piston head had to fit snugly, but not bind. Assemblers tested every gas system on firing fixtures that simulated actual shooting conditions, measuring bolt velocity and ensuring smooth operation. The trigger mechanism was a marvel of mechanical design, with multiple sears, springs, and pins working in concert to provide a clean, crisp trigger pull. The trigger group was assembled as a separate unit in a dedicated section of the factory, or where women workers, prized for their dexterity and attention to detail, fitted tiny pins through precisely drilled holes and adjusted spring tensions with hand tools. Each trigger group was test-fired on a hydraulic fixture that measured the pull weight, which had to fall between 4.5 and 6 pounds. Too light and the rifle could fire accidentally. Too heavy and accuracy suffered. The stock, the wooden furniture that the shooter held and shouldered, came from an entirely different supply chain. Walnut was the preferred wood, valued for its strength, stability, and resistance to warping under moisture. Timber came from black walnut trees, harvested in the Midwest, primarily from Missouri, Kansas, and Iowa. The logs were cut into planks at sawmills, then kiln-dried to reduce moisture content and stabilize the wood. The drying process took weeks and had to be carefully controlled. Dry the wood too quickly, and it would crack. Too slowly, and it would mold. The dried planks arrived at Springfield Armory's woodworking shop, where they were first rough cut on band saws to approximate the stock's shape. Then came the shaping process, performed on duplicating lathes that followed a master pattern and carved the wood to exact dimensions. The distinctive curve of the M1 stock, with its pistol grip and checkered wrist, was functional as well as aesthetic. It distributed recoil forces and provided a secure grip under all conditions. After shaping, the stocks were hand-finished with rasps and sandpaper, a time-consuming process that smoothed away tool marks and prepared the wood for metal fitting. Inletting, the process of carving recesses in the stock to accommodate the receiver, trigger guard, and barrel, was performed on specialized milling machines guided by templates. The fit had to be precise. Too loose, and the rifle would be inaccurate. Too tight, and the wood would crack under recoil. The stocks were treated with linseed oil, applied in multiple thin coats, and rubbed in by hand. The oil penetrated the wood fibers, providing moisture resistance and enhancing the grain pattern. Between coats, the stocks were allowed to dry and then were lightly sanded to knock down raised grain. The final finish had a soft sheen, not glossy, but with depth that suggested quality and care. Assembly brought all these components together on long benches staffed by skilled armorers. Each rifle was built individually, and not on a moving assembly line, but at fixed stations, where one person was responsible for fitting the barrel to the receiver, installing the trigger group, mounting the stock, and attaching the gas system. This approach ensured accountability. If a rifle had problems, it could be traced back to the individual who assembled it. The armorer started by threading the barrel into the receiver, using a torque wrench to achieve the exact tightness specified by engineering drawings. Too loose and accuracy suffered. Too tight, and the barrel could crack. Next came the gas cylinder, which was pinned to the barrel and checked for alignment. The operating rod was installed, and the armorer tested its movement by hand, feeling for smoothness and checking that it fully reciprocated without binding. The bolt went in next, and the armorer verified that the locking lugs engaged properly and that the bolt face was square to the barrel. The trigger group was dropped into place and pinned, and the armorer dry-fired the rifle multiple times, listening for the crisp snap of the hammer falling and checking that the safety worked correctly. The stock was fitted last, and the armorer made small adjustments with files and chisels to achieve perfect metal-to-wood contact. Every rifle then went to the test firing range, a dedicated building with firing positions and bullet traps. Armorers loaded each rifle with proof loads, cartridges loaded to higher than normal pressures, and fired several rounds to verify that the rifle could withstand stress beyond what it would encounter in combat. After proof testing, the rifles were fired for accuracy at 25 yards, and the point of impact was checked against iron sights. If the rifle didn't shoot to point of aim, the armorer adjusted the front sight by drifting it in its dovetail mount. Rifles that passed all tests received final inspection, a station where government inspectors scrutinized every surface for defects, checked dimensions with precision gauges, and verified that all markings were present and legible. The inspectors could reject rifles for cosmetic defects as minor as a small scratch or a slightly off-center stamp, and rejected rifles went back for rework. This stringent quality control was non-negotiable. A rifle malfunction in combat could cost lives, and the Army demanded absolute reliability. Accepted rifles were coated with a thin film of preservative oil, wrapped in waxed paper, and packed in wooden crates lined with moisture-resistant barriers. Each crate held 10 rifles, along with accessories including slings, cleaning rods, and bore brushes. The crates were stenciled with shipping information and loaded onto rail cars for transport to military depots scattered across the country, from the Red River Army Depot in Texas to the Sierra Army Depot in California. From these depots, the rifles moved to training bases, where recruits learned to field strip, clean, and fire them. The M1 Garand became an extension of the American soldier, carried across the beaches of Normandy, through the jungles of the Pacific, and up the frozen mountains of Korea. Its semi-automatic fire gave American troops a critical edge, allowing a rifleman to fire 8 aimed shots as quickly as he could pull the trigger, while his adversaries had to work a bolt after each round. The industrial achievement behind the M1 Garand was as significant as any battlefield victory. Springfield Armory and its contractors transformed raw materials extracted from the earth into weapons of extraordinary precision and reliability. The process demanded coordination across thousands of workers, mastery of complex manufacturing techniques, and quality control that bordered on obsessive. The rifles that resulted were more than tools of war. They were testament to American industrial capability, proof that a nation could mobilize its factories as effectively as its armies. The M1 Garand won battles, but the factories that built it won the war.